Let me introduce you NeoMaPy, a framework for computing the map inference from a temporal knowledge graph. Our approach relies on uncertain temporal knowledge graph, which are set of facts, and uncertain temporal ontologies, which are set of rules. We make them in order to produce a temporal Markov logic network with uncertain facts and uncertain rules, especially that deals temporality. The main goal of our approach is to extract from the TMLN the maximum a posteriori inference, which produces the most probable set of facts without any conflicts inside. Let's take an example with soccer with the King Pelé, who played between 56 and 77, and with different teams for which he played for, with different probabilities. One simple rule is to say that a footballer cannot play to two different teams at the same time. And there we can instantiate the ground rules that produces the complete TMLN. We compare ourselves with NRocket, which is a math inference system based on data mining, which extracts from the TMLN this map inference. It's a pessimistic approach since it's based on all the different conflicts you can have. In our approach, NeoMaPy is based on a graph-based approach, and it extracts all the conflicts, and let's say it's an optimistic approach which tries to remove all the conflicts. The main issue on that is that the conflict extraction is really computational, but all the facts are weighted, and that's a more complex approach. That's why we have a heuristic to extract all the knowledge from it. And here it is. We have the NeoMaPy approach where a given set of facts in CSV files, we obtain nodes. And then when we apply rules, we obtain a conflict graphs. What we do is to list for each node the conflicts with temporal different semantics. We remove nodes depending on which strategy is the most proper to obtain the best solution. What we have implemented behind is a database with Neo4j. We apply cipher queries to extract conflicts. Here, for instance, we have a conflict where a player cannot have two different dates of birth. Here, a player cannot play to two different teams at the same time. And the same fact cannot have opposite facts between each other. NeoMaPy has been implemented in Java, where it connects to the Neo4j database with different cipher queries that can be configured inside the system. We can remove all the graph, create indexes. The CSV file itself is pretty simple. We have node IDs, the connection with the subject, the object, and the predicate, and dates for the temporal facts. Some different facts has been added to the system. It's based on the NRocket dataset, which produces true and false facts. Some weights, since we have uncertainty in the graph. So that's it. We have imported the temporal facts, and then we have inference and certain rules in order to provide new ground rules. And then a set of conflict rules that extracts conflicts. Each query extracted the set of conflicts from the knowledge graph. And here it is. We have a complete knowledge graph with all the conflicts inside in order to see how the knowledge graph behaves. Let's have a look on it. So we use a graph stream library in order to see how to visualize the graph. So first, the layout provides an interaction between nodes based mostly on the conflicts. We have provided some colors in order to see which type of conflicts we have. And if we make a zoom on the graph, we can see the conflicts directly between the nodes, have the information between each of them. So for instance, this node has two different conflicts of type T3, which is they are older than 150 years old, which is quite a lot. And C1, where they have two different dates of birth. So the goal of the map inference is to remove some nodes in order to have no conflicts inside the graph. Here we have a different setting in which we have plenty of different conflicts, especially the purple ones corresponds to the conflicts with temporal consistency issues. So here we have partial inconsistency and some inference from the ground rules instantiation we have. And that is the one that has been instantiated. Here, have a look. We have partial consistency, partial inconsistency, and total inconsistency. So the same player has played in two different teams at the same time. According to the statistic on the graph itself, we can see that we have 90% of valid temporal facts. 10% of the temporal facts have been injected with false information. The weight of the graph is produced by the sum of all temporal facts plus the infinite temporal facts that are mandatory. What we want to obtain is a knowledge graph without any conflict inside. Let's say we have a very naive strategy to say, okay, let's take the most conflictual nodes. So if we remove them, we obtain a new graph, and the graph weight is of 9,900. And we have removed about 78% of the injected false temporal facts. A second one, which is increase in weight order, it's a less interesting one, and the false injected temporal facts has been removed with only 87%. That's better, but the graph weight is very low. So we can apply different ones and just have a look. If we only remove invalid nodes, we obtain a high graph weight, but you can see that there are remaining conflicts, just because the conflicts are not only from the false injected temporal facts, the knowledge graph itself has mistakes inside. So what we propose is a map inference where we can parameterize the fact that we can have different temporal consistency. So how much those purple conflicts can be removed. We can also parameterize our system with a threshold for the weights of the nodes. And to optimize the heuristic, we can decide the number of solutions that can be kept inside the system in order to find the most probable one. Let's have a look what's happening. Those conflicts has been extracted from Neo4j in order to compute what's happening. And then we try different solutions with combination of connected components. And here it is. What we see is we obtain 88% of invalid removed inside and a graph weight which is higher than naive strategy. If we compare ourselves with nRocket, they obtain 87%, and if we try different map inference, we obtain better results. Here is an example. We have a different map inference, but with a threshold of 0.9 and partial consistency. It's amazing just because we have some kind of conflicts that can occur. If we have a look on the global system, we can see the infinite nodes. And if we get back to the total consistency with a different setting, for instance, with a threshold of 1, no conflict is accepted. We removed some nodes, especially all the conflicts. None of them appears, and we obtain 91% of removed. Maybe we want to understand why. So for that, we can display invalid nodes and see where they are happening. And it's interesting because they occur especially in this area. And if we look at this especially, we can see that this node has not been removed. So what happened? If we just reset, it is in conflict with some nodes, but with lower weight. The maximum weight has been kept inside the system. We have made some more experiments based on performances, and we see that we outperform nRocket, especially because our system is more optimistic based only on conflicts. The more we grow the number of facts, we are more efficient. And when we add twice the number of false facts, we remain better than nRocket. So the NeoMaPy approach is a framework for computing the map inference, especially for temporal knowledge graphs. And for those knowledge graph representation, we have a tool that helps the graph interaction to explain more what's happening inside. In our approach, which is based on a graph database computation, we have an efficient map inference computation with conflict-based inference, which tries to maximize the fact that we don't want to have conflicts. So thank you for your attention, and let's have a look on the different references.